This is a screencast on assigning uncertainties to data values to recorded measurements in science and how to do that. Okay, so uncertainties, what are they? What are they for? So they are the little plus or minus values that we add to every measured data point we record in science. Okay, so in science, the ethos we want to apply is that we're only as certain as our tools are precise. Okay, we only want to record and report data based on the precision of the tool that we use to measure it with. Okay, this is just practical. It's also honest and realistic. So basically, every time we measure a data point in science, we want to make sure that we add an uncertainty value on that data point. So for example, here, a student's reaction time might be recorded as 1.1 plus or minus 0.1 seconds if recorded with a stopwatch. What's represented there is we've got the number out front, which is the actual value. Okay, that's the data point, and then we have the uncertainty written on the end of that value, which helps communicate the precision with which that value was obtained and how certain we are, thusly, about that value's precision. Okay, so how do we assign uncertainties to measurements? Well, there are a couple of set of basic rules as to how you would do this, but it's really important to acknowledge, I think, that you should realize the scientist ultimately assigns a reasonable uncertainty to values that are measured based on this set of rules. So there is some flexibility about how to assign uncertainties, but I'll show you what the basic rules are, explain those, and that's kind of what you want to apply. But it's a case-by-case basis, and mostly you want to be honest and operate with integrity, and you don't want to overstate your precision or how confidently you actually know a value that you measure. So the first rule here is this one that you can see right here, that measuring with an analog device, so that basically means a non-digital device, something that's not battery powered, something that you don't plug in, something that doesn't have a screen where you're reading a value, but rather a tool like a classic mercury thermometer, alcohol thermometer, a piece of glassware like a graduated cylinder or a burette or a pipette. An analog device, you're supposed to use half the smallest graduation on the device, and that's what you, as a standard, assign as the uncertainty. So if you have a look here, for example, if you're using this graduated cylinder, okay, that I've drawn here, if each tick, okay, so by the way, the graduation is, that might be what we would think of as like a tick on the thing, on the scale. So if each tick is 1 milliliter on this graduated cylinder, and that represents an amount of water in there, we might see that it's over the 5 ml tick, but it's not all the way to the 6. And so you want to estimate this digit, okay? You always estimate one more digit than the scale gives you, okay? So you estimate that digit, and then as such, and according to the rules of uncertainty, you assign uncertainty in half the smallest graduation that is on the scale. So since it goes to 1 milliliter, you want to make sure you assign a half a milliliter uncertainty by default. Okay? So there's your uncertainty you put on it following the rule. Now you can step back from this and say, well, what does this, if you think about what this actually means or what this whole thing actually communicates, we're saying that our confidence of this value, 5.3 milliliters, we could add 0.5 to it or we could subtract 0.5 to it. So in a way, you could think of it as saying, well, it's somewhere between, 4.8 and 5.8. And then you might look back at this and be like, well, hey, this value is not 4.8. I'm more confident than that. It's definitely over 5. So there is some wiggle room. You could reduce that uncertainty a little bit depending on the situation. But usually devices are designed so that it is really difficult to have more than like a half a unit of confidence in between the marks, if you know what I mean. If I'm kind of losing you here, that's okay too, but basically follow the rule and put a half of the smallest graduation. The other one thing I would mention here that I think is important to consider is that you'll notice we've got uncertainty in the same place value as the most precise digit recorded. Okay, that's a good alignment. That's a rock solid alignment. If we had uncertainty in a value like this, if we said like, oh, it was 5.3 plus or minus 1 milliliter, well, now we have like a bit of a logical fallacy here, because if you look, if you're uncertain in the ones digit, right, then definitely the tenths digit is completely meaningless, right? If we're admitting that we're uncertain in the tenths, in the ones, then clearly we have no idea what the tenths digit is. It'd be like saying, how far is it to drive from Victoria, BC to Port Hardy, BC, and saying, it's around 600 kilometers. And then someone saying, oh, but how many meters on top of that 600 kilometers? And you're like, I'm not even sure about the kilometers. Obviously, I'm not certain about the meters. So when you increase in precision, there's no way you'd be more certain about that. So you want to make sure you're assigning uncertainty in the most precise place value that is presented. Rule number 2, for a digital device, okay, so something, as we discussed earlier, that's plugged in or has a battery, gives you an actual numerical digital readout. For a digital device, you want to make sure that the last digit is presented as uncertain, okay? So that the most precise digit is presented as uncertain. For example, if you're taking a mass reading of something off of a digital mass balance, sometimes colloquially known as a scale, a mass scale, although you shouldn't really use that term, but we all know what you mean when you say a scale. Not very scientific, but the best thing to call it is a digital mass balance. But when you're taking a value off a digital mass balance, and maybe the balance reads 2.38 grams, well, what you should write is, as you see here, 2.38 plus or minus 0.01 grams. Okay, that acknowledges the fact that we're only so certain about that place value, okay, because that wasn't about that place value, because that is as precise as the scale is, as the mass balance is, right? So you would at least put that much uncertainty. Now I say at least because sometimes you look at, for example, the output, the reading from a digital mass balance, and it'll kind of fluctuate. It'll say 2.37, 2.38, 2.39, 2.41, 2.3. You know how it kind of doesn't come to rest very easily, and this is something that happens naturally because there can be some fluctuation, and there can just be general imprecision in the device. So you can also, if you see it fluctuating a lot, you can also change or increase the uncertainty that you assign, because you can represent that fluctuation. So maybe you want to put something like, well, the 2.38 was kind of a middle value, but I'm going to assign a little bit more. I'm going to say it was actually more like plus or minus 0.03 grams based on the fluctuation. Also worth mentioning is there are essentially two ways you can record uncertainty, and this is also based in some practicality because you can quickly communicate a little bit more about how precise a value is based on converting the absolute uncertainty, what we call the absolute uncertainty, into what we call the relative uncertainty. Okay, so an absolute uncertainty is when the uncertainty is in the same units as the value. So that's what we've looked at so far. For example, when you see 3.7 plus or minus 0.5 centimeters, that's an absolute uncertainty. Both the uncertainty and the value are in the unit of centimeters. Okay, a relative uncertainty kind of actually does a little bit of analysis and says, like, based on that absolute uncertainty, how precise really is this measurement of 3.7 centimeters? And so it's the uncertainty expressed as a percentage of the value. So you take the uncertainty and you divide it by the value, okay? And then you're going to get what proportion of the value the uncertainty is, and we generally express that as a percentage. So if you do it here, you put 0.5 over 3.7, that equals 0.135, dot, 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 a whole bunch of figures. Don't worry too much about the significant figures, but ultimately, if you were expressing it as relative, you would say the relative uncertainty here is 13.5% uncertainty. So that means actually, even though 0.5 centimeters doesn't seem like that much uncertainty, compared to the value you were measuring, 3.7, it's pretty large, 13.5% uncertainty.